A blockchain can keep producing blocks, validators can keep agreeing, and every past transaction can remain visible. Yet, somebody could still steal from wallets by forging their signatures. That is the future risk Near is trying to address with its 2.13 mainnet upgrade, activated on July 20th, 2026. The network now supports an optional post-quantum signature system called ML-DSA 65. The short answer is yes, a blockchain can give wallets protection against a future quantum computer, but installing support at the network level is only the first step. Users need compatible wallet software, and they need to add a quantum-resistant key. In some cases, they also need to remove older keys that remain vulnerable. So this does not make every Near account magically quantum safe. It creates a migration path. To understand why that matters, think about what your wallet actually does. Your wallet does not store coins like files on a phone. The blockchain stores a record saying which account controls which assets. Your wallet stores private keys that can authorize changes to that record. When you send a transaction, the wallet builds a message containing details such as the sender, receiver, amount, recent block information, and a nonce. It then produces a digital signature using your private key. Network nodes verify that signature using the matching public key. If the signature is valid and the transaction follows the rules, the network can process it. If someone changes even a small part of the message, verification should fail. Bitcoin, Ethereum, Solana, and most other blockchains depend heavily on elliptic-curve cryptography for this process. The exact signature scheme varies, but the security assumption is similar. Given a public key, an ordinary computer should not be able to calculate the corresponding private key within any practical amount of time. A sufficiently capable quantum computer could change that assumption. Shor's algorithm provides a way for a large, fault-tolerant quantum computer to solve the mathematical problems protecting widely used elliptic curve signatures. That does not mean a laptop with a few quantum chips can empty wallets. There is no public evidence of a quantum computer capable of performing this attack against major blockchains today. The machines required would need to be far larger and more reliable than publicly demonstrated systems. The problem is that blockchain migrations take time. Wallets, hardware devices, exchanges, custody systems, smart contracts, validators, and users may all need updates. Waiting until an attack becomes practical would leave very little room for mistakes. And unlike encrypted private messages, blockchain activity is permanently public. Public keys that have already been revealed can remain visible for years. An attacker does not necessarily need to collect data secretly in advance. The chain has already preserved much of it. If you enjoy explanations that separate what a protocol really does from what the headline suggests, consider subscribing. Now, let's look at what Near actually changed. Near added ML-DSA 65 as a third supported signing scheme alongside ED 25519 and SEP 256K1. ML-DSA stands for Module Lattice-Based Digital Signature Algorithm. It was standardized by the United States National Institute of Standards and Technology in FIPS 204. Instead of relying on the elliptic curve problem that a powerful quantum computer could solve, ML-DSA relies on mathematical problems involving structured lattices. No practical classical or quantum attack is known that can efficiently defeat the standardized scheme when it is implemented correctly. The phrase quantum safe needs some caution though. It means designed to resist the known capabilities of quantum algorithms. It does not mean mathematically guaranteed to survive every future discovery. Cryptographic standards can be revised, implementations can contain bugs, and new attacks can appear. NIST approval means the design has gone through a major public standardization process. It is not a promise of permanent invulnerability. Near's account design makes this migration unusually interesting. A named Near account, such as alice.near, is not permanently fused to one cryptographic key. The account can hold multiple access keys, and authorized transactions can add or remove them. Some keys can have full access. Others can be restricted to calling particular smart contracts. Most importantly for this upgrade, those keys can use different signature schemes while controlling the same account ID. Imagine Alice currently controls alice.near with an ED25519 full access key. She wants to move to ML-DSA 65. First, Alice uses supported software to generate a new ML-DSA key pair. The private key remains in the signing environment. That could eventually be a wallet or hardware device, although consumer integration is still developing. Next, Alice creates a transaction that adds the new ML-DSA public key to alice.near. Her existing ED25519 key signs that transaction because it currently controls the account. The network verifies the old signature and records the new access key. Since an ML-DSA 65 public key is 1,952 bytes, Near does not store the entire public key in the account's on-chain key list. It stores a 32-byte SHA-3 256 hash of that key instead. When Alice later sends a payment with the new key, her wallet builds the transaction and signs it using the ML-DSA private key. The transaction provides the information needed for nodes to identify the public key and verify the signature. Nodes hash the public key, confirm that its hash matches an authorized access key on alice.near, and then check the ML-DSA signature. If every check passes, the transaction continues through Near's normal processing system. Alice keeps the same account name, balances, contract state, and history. She changes the authorization method rather than moving everything to a new identity. But there is one crucial final step. If Alice leaves her old full-access ED25519 key active, an attacker who can break that older key may still control the account. Adding one strong lock does not help if a vulnerable lock beside it can open the same door. For stronger post-quantum protection, Alice would use the authorized ML-DSA key to remove the old full-access key after confirming that the new setup works, and that she has a safe backup. That transition must be handled carefully. Removing the wrong keys can lock an account permanently. This is one reason the feature is optional. The network understands ML-DSA transactions, and developers can manage the keys using Near's command line tools and supported libraries. That is not the same as saying every mobile wallet, browser wallet, exchange, custodian, and hardware signer is ready. The new signatures are also much larger. An ML-DSA 65 signature is 3,309 bytes, while common classical blockchain signatures are far smaller. Larger transactions consume more bandwidth. Verification requires additional computation, and Near charges extra gas for ML-DSA verification to reflect that cost. The protocol reduces account storage overhead by keeping only a hash of the large public key on-chain, but it cannot make the signature itself disappear. Quantum resistance comes with a real data and processing trade-off. There are also parts of Near that this upgrade does not protect. The current post-quantum support covers account access keys and transaction signing. Near's documentation says validator keys, block production, and implicit account addresses continue to use ED25519. So calling the entire network fully quantum-proof would be inaccurate. Users can protect certain account authorization paths, but the blockchain still has classical cryptography elsewhere. A complete quantum migration would be a broader project involving consensus keys, infrastructure, recovery systems, bridges, and every important integration. The same 2.13 upgrade also introduced dynamic resharding. This feature is not part of the quantum defense, but it addresses a different long-term problem. A shard is roughly a portion of the network's state and workload. Instead of making every validator process every account in one giant lane, a sharded blockchain can divide the work across multiple lanes while maintaining one coordinated system. Before dynamic resharding, changing Near's shard layout required a protocol upgrade with validator coordination. Under the new system, a shard can split automatically at an epoch boundary when its runtime state grows beyond the configured threshold. The split is deterministic, and validators use state witnesses to confirm the transition. Think of a warehouse divided into sections. When one section becomes too full, the system can reorganize it into two sections without scheduling a company-wide rebuilding project. This does not guarantee that every application becomes infinitely fast. Cross-shard communication still has overhead. Validators still need adequate hardware and network capacity. A popular contract may also create a local bottleneck that adding shards does not instantly solve. Still, automatic splitting gives the protocol a way to expand state capacity without hard-coding every future shard layout. It also shows why upgrades like 2.13 are about preparation rather than one immediate crisis. One feature prepares the authorization system for a possible cryptographic transition. The other prepares network structure for changing demand. What does this mean for Bitcoin, Ethereum, Solana, and other chains? It does not mean they are suddenly broken. It means every blockchain needs a credible answer to cryptographic migration. Some systems may introduce new transaction types. Ethereum can use smart contract accounts and account abstraction to support alternative authorization rules. Bitcoin could adopt new script capabilities and move funds to quantum-resistant outputs. Other networks may support hybrid signatures that require both classical and post-quantum proofs during a transition. Each option has costs. Users may need to move assets, addresses may change, and old funds may remain exposed. Larger signatures can also reduce network capacity. Governance can be just as difficult as the cryptography because millions of people must agree on when and how to migrate. Near's main advantage here is not that quantum computers can never threaten it. The advantage is that named accounts and rotatable access keys let users change the lock without automatically changing the account itself. The 2.13 upgrade therefore answers one question and raises another. A blockchain can support quantum-resistant wallet signatures in production. The harder challenge is getting wallets, devices, services, and users to adopt them before that protection is urgently needed. If you have questions about post-quantum wallets, access keys, or dynamic resharding, leave them in the comments and tell us which crypto mechanism you want to explain next.